Thank you. All right, so last lecture, we talked about collocation using LG points. Now, if you remember, the way we had done this was that the interval from -1 to 1 was set up as follows. We had the Gauss points, which were on the interior of the interval -1 to 1. And then, let's make sure I have the right number. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, yeah, that's right. And if you remember correctly, the first Gauss point, which is this one right here, was tau 1, and it was greater than -1. The last Gauss point, which was here, is tau n, and it was less than +1. And what I had said was that we constructed a state approximation which included these points, but we also included this endpoint at tau equals -1, and we defined this as tau 0. And then we also included another point at the end, which I called tau n plus 1, which is equal to +1. And the way we wound up constructing the method was that x of tau, which is the state on -1 to 1, was approximated by this function capital X of tau, which was equal to the sum from I equals 0 up to n of xi li of tau, where we included the initial point in the state approximation. So the state approximation, if you remember correctly, the state approximation uses n plus 1 points in the case of LG collocation. And then what we did was we constructed from this, we had the state approximation, the derivative of the state approximation, which I called x dot of tau, was equal to the sum from I equals 0 up to n of xi times li dot of tau. And what happened was that because we only have n quadrature points, those being the Gauss points, we collocated this state approximation at the n Gauss points. So this became f of xj and uj, and this was for j going from 1 up to capital N. And in the process of doing that construction, we noticed that this differentiation matrix, which we can call dij, which is equal to li dot of tau j, was equal to, well, actually I called it dji, if I remember correctly. I did it this way. And what we got was we got this matrix where I went from 1 up to, from 0 to n, and j went from 1 up to n. So what happens is that this matrix that we construct, dji, if you notice, dji, if I put it in matrix form, is a matrix of size n by n plus 1. And we divided this matrix, I called the whole matrix D. And we divided D into its first column and into columns 2 through n plus 1, which I labeled 1 colon n. And what we observed was that when we did this collocation in this manner, we got a system of equations that looked like this. It looked like D times x is equal to f of 1 colon n, where this matrix x was actually equal to x0 all the way up to xn, where each of these, of course, are row vectors. So we wound up with a system that actually had more points, one more point on the left side than on the right side. So we were able to decompose the system as follows. We were able to decompose it as d0 times x0 plus d1 colon n times x1 colon n is equal to f of 1 colon n. And then I said that that system that we got actually has an equivalent integral form, where the integral form looked like this. It looked like x of 1 colon n is equal to this matrix A 1 colon n times f 1 colon n, and then plus 1 times x0, where I made the observation and I said that these results had been proven that a of 1 colon n was equal to the inverse of d of 1 colon n. And this matrix, this column vector 1, was actually constructed by minus d 1 colon n inverse times d0. So these two things were equivalent. So basically, this Gauss pseudospectral method had was an integral method because this is obtained by quadrature approximation of the state at each of the Gauss points, and it's equivalent to the differential form, which is obtained by taking that state approximation and differentiating it and collocating at the n LG points. So these two forms are exactly the same. And it turns out that even though we write this as a derivative method, it actually turns out that it is a quadrature method. It's a Gaussian quadrature method. So now, that's the summary of the LG method. What I'm going to go on to do now is we're going to talk about collocation using LGR points. Now, collocation using LGR points is actually easier in some ways than using LG points. It seems kind of strange because you think that, well, maybe this isn't going to work out with LGR points. So let's look at the schematic when we change now to LGR points. Now, if you remember the LGR points, there's a collocation point at -1, and then there are these LGR points on the interval -1 to 1, but the last LGR point does not include +1. So tau n is less than +1. And this point right here is tau n plus 1, which is equal to +1. This over here is tau 1, which is now equal to -1. So the LGR set includes one of the endpoints, but it doesn't include the other endpoint. And so you could see again, just like with LG, except for there's a slight difference here between the two. If you go back over to the LG situation, you see that we actually had two endpoints that were not in the set. So what happens is that we actually have to account in the Gauss method, we have to account for the last point by using a quadrature approximation to the integral across the entire interval, which actually gives us this equation times where this is the state, where xn plus 1 is the state at the final point, and we add that in as an additional equation into the method because now we account for all endpoints. In this case, though, we only have one endpoint that is not a collocation point because the quadrature points include the initial point. So what we do is we construct a state approximation as follows. So the state approximation using Redau is done in a manner similar to what we do for Gauss. Remember, for Gauss, we took the initial point and we added it in as an approximation point in the polynomial approximation. Well, we have an additional point in this case too, so we add it in as a point in the approximation. So what we have is we have x of tau, which is the state, is approximated by now we've got x, capital X of tau, but in this case now the sum goes from I equals 1 to n plus 1 xi times li of tau. Now, if you look at this, you see that I'm summing from 1 to n plus 1 because I'm always denoting the collocation points as 1 to n. They're always going 1 to n. So in the case of Lobato, tau 1 is equal to -1. Tau n is actually equal to +1. In the case of Gauss, tau 1 is equal to the first Gauss point, and tau n is equal to the last Gauss point. And in this case of LGR, the first Redau point is actually at tau equals -1. So the first point in this set is tau 1 equals -1. And then there's a non-collocated point at n plus 1. So we sum from 1 to n plus 1. Now you notice in this summation we have n plus 1 points. So this is a polynomial of degree. It's a polynomial of degree n. And the reason it's a polynomial of degree n is because this basis, Li of tau, is actually equal to the following. It's equal to the product from j equals 1 to n plus 1. J is not equal to I. Tau minus tau j, tau I minus tau j. So these are nth degree polynomials. So we have a state approximation that's a polynomial of degree n. So what we do is we say, all right, now I'm going to erase this Gauss picture now because I'm done with it. I don't need it for anything. So if I differentiate that approximation, what I get is I get the following. I get that x dot of tau is equal to the sum from I equals 1 up to n plus 1 of xi li dot of tau. And of course, we know that this is approximately the derivative of the state. Now, if you look at this, you see that if that polynomial over there is of degree n, then when I differentiate a polynomial of degree n, I get a polynomial of degree n minus 1, just like I did for Gauss. So I've got x dot of tau is a polynomial of degree n minus 1. Now, again, as you saw with Gauss, we started with a polynomial of degree n, differentiated it, got a polynomial of degree n minus 1, and we collocated that polynomial at n points. In the case of Redau, we have exactly the same setup as far as the collocation goes. We have n Redau points, right? So we have n Redau points. So if we write all this down, we see the following. So we have n LGR points. And we know that x dot of tau is uniquely defined using n points, right? Because it's a polynomial of degree n minus 1, so it's uniquely defined using n points. So we can collocate x dot of tau at the n LGR points. And we wind up with the following result, which is that x dot of tau j is equal to f of xj uj. And now, we go from j equals 1 up to n. So now let's look and see what happens when we actually use that approximation. Or, sorry, that we collocate that derivative using the approximation that we've constructed for the Redau method, which is that we get the sum from I equals 1 to n plus 1. And here we get xi li dot of tau j is equal to f of xj uj. So now, let's look at this. So you can see here again that on the left-hand side, I'm using n plus 1 values of the state, right? So let's say left-hand side. We use x1 all the way up to xn plus 1, right? Now, if you look at that, we know that x1 is equal to the state approximation at tau equals minus 1. And line this up, xn plus 1 is equal to the state approximation at tau equals plus 1. So what I have here is I've already accounted for all of the values of the state, including the endpoints. So not just the LGR points, but I've got the LGR points plus the final point. And the final point is at plus 1. So I have both boundary points included in this system of equations here. So now if I construct the matrix dji, if I call it li dot of tau j, right? So this is now j going from what? If you look at the j goes from 1 to n, so let's do it I first. So I goes from 1 up to n plus 1, and j goes from 1 up to n. So what I have here is I get the sum from I equals 1 to n plus 1 of dji xi is equal to f of xj uj for j going from 1 up to n. So now, if I put that together in matrix form, where again we define everything the same way that we did for Gauss, which is that I construct x. In this case, x is going to equal x1 all the way up to xn plus 1, right? And I mean, if you just follow this logic through, you get x1 through n is equal to x1 up to xn. And the same thing with u. You get u, which is being evaluated at 1 to n, is equal to u1 all the way up to un. And then lastly, you do the same thing for f. F is only evaluated at the quadrature points. So you get f1 all the way up to fn, where these are abbreviations. F1 is f of x1 u1, and f2 is f of x2 u2, etc. So if you take that, now what you do is you make the matrix D, because the way I'm doing my notation is I'm going to keep it consistent with the way I'm doing the indexing over here. So I've got D is D1 and then D2 through n plus 1. So in this case, the differentiation matrix consists of a first column and then the remaining n columns. So D1 is the first column of D. And D2 colon n plus 1 are the remaining n columns of D. Okay, now let's embellish this just a little bit more. So if I take this system and I break it up, what I get is I get D1 times x1 plus D2 through n plus 1 x2 through n plus 1 is equal to f1 through n. So you can see now that system looks almost exactly the same as the system that we got when we did Legendre-Gauss. The difference is now that in the case of Legendre-Gauss, we were missing the final point in that system because the state approximation only included the initial point plus the NLG points, whereas in this case, the state approximation includes the LGR points plus the final point. So this system here includes all of the points. So if I take this system, so the collocation equations include the n LGR points plus the final point, right? So we've got this really nice setup where now we don't have to add another equation in order to get the quadrature, because whereas in Gauss we had to estimate the final state by Gauss quadrature, there's no need to do that here. We already have that final state included. Now, if we go back to the integral form, so now let's look at it the other way. Let's look at the integral form, because this is again, it's kind of a strange thing. But we know that x of tau is equal to the integral from -1 to tau of f of x of s u of s ds, right? So now if tau1 through, so now what we're going to do is we're going to do an integration the following way. So suppose we integrate from -1 to tau j, where in this case j goes, let's put it on the next line, where the index j goes from 2 through n plus 1. I can do that in this case, right? Because I have n plus 1 points in my approximation. I can use them the way I see fit. I'm going to integrate up to from the first from the initial point to the first interior Redal point. So what I'm going to do is so this is at -1. So I'm going to integrate from here to there, and then I'm going to integrate to the next point, to here, and then I'm going to keep integrating. I'm going to integrate to here, and then finally, I'm going to keep doing this until I get down to the end, where I'm going to integrate across the entire interval, right? So if you look at this, this is tau 2, tau 3, dot, 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 all the way up to tau n plus 1. So I'm integrating from tau 2, -1 to tau 2, -1 to tau 3, all the way up -1 to tau n plus 1. If I do that, then what I wind up getting is I get this. I've got x of tau j is equal to the integral from -1 to tau j, f of x of s, u of s, ds. And this goes, again, j goes from 2 up to n plus 1. All right, so that's all cool, right? So now what we can do is we can approximate this integral by quadrature. So we do the same thing that we did before, which is that I know, and maybe I'll get a little bit more formal here so everyone can see this a little bit more clearly, which is that we know that, I did this with Gauss, but I'll do this again with, I'll do this with Redal a little bit more explicitly. We know that s in this integral, it's a dummy variable of integration, but it goes from -1 to tau j, right? So that means that s plus 1 goes from 0 to tau j plus 1, which means that s plus 1 over 2 goes from tau j plus 1 from 0 to tau j plus 1 over 2. So how am I going to get this interval to map to -1 to 1? Well, the way that we can do this is if I do the transformation, you see that suppose I want to start with -1 to 1. So let's go -1 is some new variable. Let's call this new variable zeta. Goes from here to there. So now I go 0 is less than or equal to zeta plus 1, which is less than or equal to 2, which says 0 is less than or equal to zeta plus 1 over 2, which is less than or equal to 1, which says that 0, if I multiply this out, now let's see here. Actually, wait a second. Let's do it this way. So I got 0 is less than or equal to zeta plus 1 over 2, which says that, hang on a second. Let me do this the other way. Let's start over again so I can make sure I do this right. I know that s goes from 0 to, from -1 to tau j, right? So what I want is I want to transform this to the interval -1 to 1. So we want zeta on the interval -1 to +1, because that allows me to be able to use a standard quadrature, right? So if zeta is my variable that goes from -1 to +1, what I want to do is I want to transform this to the interval to tau j plus -1 tau j plus 1 over 2. So what you can do is you could say that -1 is less than or equal, 0 is less than or equal to zeta plus 1, which is less than or equal to 2. So that says 0 is less than or equal to zeta plus 1 over 2, which is less than or equal to 1. So if I just multiply this by tau j plus 1 over 2, I got 0 is I'm having so much trouble with this. Let's see. Tau j plus 1 over 2. I'm sorry. Well, let's try this one more time. I'm having a really hard time doing this transformation. I don't know why. So I know that here, this is 0 is less than or equal to s plus 1 is less than or equal to tau j plus 1, which says that 0 is less than or equal to s plus 1 over 2, less than or equal to tau j plus 1 over 2. Okay, I'm almost there. So now what I can do is I want this interval to go from -1 to 1. So if I take the integral from -1 to tau j of, say, x, say f of x of s, u of s, ds, that's equal to, now I get a scale factor in front, which is I get tau j plus 1 over 2, the integral from -1 to +1 of f of x of zeta, u of zeta, d zeta. Let's just make sure that that is in fact correct. I'm still not 100% sure that's right, but let's do it slowly. So I want zeta on -1 to +1. So that says that zeta, when I'm all done, has to give me something that's between -1 and +1. So, and I have the interval of s, which goes from -1 to tau j plus tau j, right? That's what I actually have. I don't have tau j plus 1. I've just got tau j, right? So if I want this interval to go between -1 and 1, if I add 1 to it, I get this, right? And so now I want this interval to be transformed to that interval up there. So if I transform this by dividing through by tau j plus 1, what I get is 0 is less than or equal to s plus 1 over tau j plus 1, which is less than or equal to 1. So I get 0 is less than or equal to 2 times s plus 1 over tau j plus 1, which is less than or equal to 2, which says that -1 is less than or equal to 2 times s plus 1 over tau j plus 1, which is less than or equal to 1. That's the transformation I was looking for. OK, so now, you could see that if I use that transformation, right, because that gets me on the interval -1 to 1. So zeta is equal to 2 times s plus 1 over tau j plus 1, which says that d zeta ds is equal to 2 over tau j plus 1, which says that ds d zeta is equal to tau j plus 1 over 2. So now I can plug that in to that equation over there, and I've got the integral from -1 to tau j of x, f of x of s, u of s ds is equal to, now if you do the substitution, you get tau j plus 1 over 2, the integral from -1 to 1, f of x of zeta, u of zeta, d zeta. So now this interval goes from -1 to 1. So because I'm using Legendre-Gauss-Radal quadrature, this can be approximated using the following quadrature rule, which is tau j plus 1 over 2 times the sum from I equals 1 up to n, right? Well, now wait a second. Now you got to be careful here. This is a Radal quadrature. So yes, so this is wj or wi times fi. So each of these can now be transformed to an interval which goes from -1 to 1. And now what we get is we get these coefficients which basically look like this, which is that the value of the state approximation at each of these points, j going from 2 to n plus 1, is going to equal tau j plus 1 over 2 times the sum from I equals 1 up to n of wi times fi, which can be rewritten as, if I just multiply through by tau j plus 1 over 2, I get the sum from I equals 1 to n of, well, actually, sorry, there's an initial condition in here, plus x1. So I've got to be careful over here, too. There's also an initial condition over here, plus x of -1. I've got to account for that initial condition. So now, when you put all this together, you get x1 plus the sum from I equals 1 up to n. So if I put these together, tau j plus 1 over 2 times wi, now I have a weight which gives me alpha ji fi, right? Where alpha ji is equal to tau j plus 1 over 2 times wi. So now this goes from 1 up to n. So if I do this now, what are the indices? I know that I goes from 1 up to n because that's the summation. J goes from 2 up to n plus 1. So what I do is I wind up constructing this system over here, which looks like this. I get x2 all the way up to xn plus 1 is equal to a column vector of 1s times x1 plus, I get this matrix here, which is this matrix of alphas, which gives me alpha 1, 1, alpha 1n, alpha n1, alpha nn. And this whole thing gets multiplied by what? It gets multiplied by f2 up to, f1 up to fn. So when I put all this together, what I get is I get x2 through n plus 1 is equal to 1 times x1 plus, I get this matrix A, 1 or 2 through n plus 1, because you'll see that the indices on this thing run differently from the indices on the matrix over here. You see that j runs from 2 to n plus 1. So really, this should be, this whole thing here, even though I've labeled it this way, it goes from 2 to n plus 1. So I should probably label it that way. I should go 2, 1 up to n plus 1, comma 1. And I've got 2n up to n plus 1, comma n. So this gives me a matrix A2 colon n plus 1 times f of 1 colon n. So now if you look at that system and you compare it to the differential form, so if you remember the differential form looked like as follows. It looked like d1 times x1 plus d2 colon n plus 1 times x2 colon n plus 1 is equal to, now if I put this here, I've got f of 1 colon n. So you see that the systems, again, look exactly the same if it turns out, so if the following is true, if d2 colon n plus 1 inverse is equal to a 2 colon n plus 1, and these other things are true too, which is that 1 is equal to minus d2 colon n plus 1 inverse times d1. If these things are true, then the integral and differential forms are equivalent. Well, it turns out that just like for Gauss, in the case of Radau, they are in fact equivalent, which is that these things are actually equal to each other, and it's the same thing as what you get. And what you see here is that you'll notice something in this integral form. If you look at the last row of integral form, what you get is this, is you've got x n plus 1 is equal to x1 plus, now if you look at that, let's just pull the last one out. We've got the sum from I equals 1 up to n of alpha n plus 1, 1, or alpha n plus 1 I, times what? Times fi, right? Because I'm fixing the last value. So you can see what happens here. In the last row, you've got the value of the state at the final point is equal to the value of the state at the first point plus a summation that goes from 1 to n, and it includes a bunch of weights. But remember that the last point, tau n plus 1, is actually equal to plus 1, right? So that means that tau n plus 1 over 2 is equal to plus 1, which means that this equation right here reduces to the Radau quadrature, which is x1 plus the sum from I equals 1 to n of wi times fi, where this is the standard LGR weight on minus 1 to plus 1, which means that the last equation is, in fact, the Radau quadrature. So we don't have to actually include another equation to get the last state because it's already been included, and it turns out that it is obtained by Radau quadrature. So by simply using the state approximation in the manner that we've actually constructed, which includes the n LGR points plus the final point, we automatically get the final point as an approximation point in the collocation equations, and it turns out that that last point is actually computed by Radau quadrature. So the summary of this looks like this. If we take LG and LGR, here's what the summary comes down to, is that when you look at the two systems, So what I'm going to do is I'm going to write on this board, I'm going to split it in half, which is that when we do LG, what we have is we've got D0 times X0 plus D1 colon n times X1 colon n equals F1 colon n. And the final state, which is xn plus 1, is equal to x0 plus w transpose times f1 colon n. Right? Now, if we look at the variables in this problem, the variables are as follows. We've got the state at the Gauss points plus the final point. If you look in these equations, you'll see that it includes all this information. But the control is only approximated at the Gauss points, right? So the control is not approximated at the initial point or the final point, which means that we have no control or no value, or no variable for control at either tau equals -1 or tau equals +1. Now let's go over to LGR. Let's look at the difference. With LGR, the system looks like this. We've got D1 times X1 plus D2 through n plus 1 times X2 through n plus 1 equals F1 colon n. We still get that F of 1 colon n. But now we don't need another equation to give us the quadrature at the, to estimate the state at the final point, because it's already included in this system here. The variables in this problem, if we do the formulation this way, are x1 up to xn plus 1. So you can see here that in this case, x1 corresponds to the value of the state at tau equals -1, and xn plus 1 corresponds to the state at the final point. So we've got all the values of the state at both endpoints plus the interior points in the quadrature. And the variables on the control actually go from u1 up to un. Now don't be deceived by this though, right? u1 through un in this case are the LG points. u1 through un in this point, in this formulation, are the LGR points. So the LGR points include -1. So in this case, we have a variable for the state at, for the control. For the control at tau equals -1, but we do not have a variable for the control at tau equals +1. But in both cases, so now I can do this. In both cases, it doesn't matter which case we take. Both the LG, both the LG and LGR collocation schemes are Gaussian quadrature approximations. So it doesn't matter which one we use. In the case of Gauss, we're using a Legendre-Gauss quadrature. In the case of Radau, we're using a Legendre-Gauss-Radau quadrature. And so you can see that it doesn't matter which one of these you use, you're going to get a Gaussian quadrature approximation to the integrals in both cases. So what's the difference? Well, you remember that Gauss, right? The Gauss quadrature, so let's write this down. The LG quadrature is exact for a polynomial of degree 2n minus 1 or less, right? The LGR quadrature is exact for a polynomial of degree 2n minus 2 or less. So think about what we've gained and what we've lost in the process of doing these two methods. In the case of Gauss, we get 1 degree higher accuracy for n LG points than we do using Redao for n LGR points. So if I use n LG points, I'll get one polynomial. I can integrate a polynomial 1 degree higher, exactly. But in the process of doing this, we don't actually get a value of the control at the initial point. So if we schematically look at this, let's look at the control approximation. Let's look at the control variables. So in the case of LG, what we have is we have the control at the LG points, right? 1, 2, 3, 1, 2, okay. I just schematically, right? So this is where U1 is, and this is where UN is, right? So there's no control here, and there's no control there. In the case of LGR, we have this added benefit that I get the approximation of the control. This is -1, and this is +1. I get the control at the initial point, and then I get the control at all these LGR points, right? Whatever they happen to be. This is U1. And this is UN. So the benefit of using LGR as compared to using LG is that in the case of LGR, I get the control at the initial point. Now, if we're doing control, if we're thinking about this in the sense of feedback, you would like to have the control at the starting point, right? You don't want to have the control at some other point because we don't have a function, a unique function that approximates the control. The only thing we have is a unique function that approximates the state. So anything we do to get the control is going to have to be done by extrapolation, which is not going to be, at best, it's going to be a guess, right? If I do linear extrapolation or I do cubic extrapolation or a Lagrange polynomial extrapolation, it doesn't matter which one I do. It's going to be an estimate, which is going to be wrong because I don't have a variable at that point. So clearly, it would be preferable to have a scheme that actually has a variable at the initial point. So Redao has all the benefits of Gauss in the sense that it's a quadrature method and it's a Gaussian quadrature method. The only thing it suffers from is that it's 1 degree less in accuracy than Gauss. Well, that's not a very big deal, right? If you think about the overall accuracy of your scheme, if you lose 1 degree in exactness in the quadrature of a polynomial, that's a small price to pay to be able to get a value of the control at the initial point. But like I said, in both cases, both the LG and LGR collocation schemes are Gaussian quadrature approximations. Okay? And that's very important because if you remember, I said that Lobato is not a Gaussian quadrature approximation. And as a result, you don't even have an integral form for Lobato. Lobato doesn't follow the rules that Gauss and Redao follow. So hopefully this will give you a starting point to be able to think about how to conceive some of these, how to use some of these methods. I'm not going to, I'll maybe next lecture what I'll do is I'll go through the more general formulation where you have an interval from from T0 to TF. I'll map it to -1 to 1, and I'll show you that nothing fundamentally changes if you change the interval from T0 to TF. You just get a scale factor of TF minus T0 over 2 in front of everything, and all the equations stay exactly the same. And really, and you could see that. Maybe I'll finish that just now. Actually, I have enough time to be able to do it. So let me just do it. So let's suppose now we just go to a regular interval from T0 to TF. So let's just go back to this Lagrange formulation of Bolzano formulation of the optimal control problem, and I'll just show you real quick that this actually doesn't change at all if you go from T0 to TF. So if your cost function is equal to phi, which is a function of x of tf, and x of t0, t0, x of tf, and tf, and then plus the integral from t0 to tf of L of x of t u of t dt, what we see here is that because this interval tf, this integral can be equivalently written as tf minus t0 over 2 times the integral from -1 to 1 of L of x of tau u of tau d tau. It's the same transformation that I had earlier. It's just that now I'm doing it from -1 to 1. So this is what this can be approximated by quadrature, right? And then the same thing for phi. What I can do with phi is I can replace phi equivalently with x of -1, t0, x of +1, and tf. So nothing changes there. So they're exactly the same as what they were before. It's just that now I'm mapping it to -1 to 1. The dynamics, I've got dx dt is equal to f of x of t u of t. And if you look at that, you can see that that just gets written as follows. If I change to the interval -1 to 1, so I let tau go from -1 to 1, I've got dx dt is equal to dx d tau times d tau dt, which is equal to f of x of tau u of tau. And now I introduce t0 and tf in here because they're going to be functions. And so what I'm going to get is I'm going to get dx d tau is equal to dt d tau times f of x of tau u of tau. And then I introduce these parameters again, t0 to tf. But dt d tau is just equal to tf minus t0 over 2 times f of x of tau u of tau, and then t0 and tf. So nothing actually changes. You see that I've just got everything mapped onto the interval -1 to 1, and I've got this scale factor of tf minus t0 over 2 in front. Everything else stays exactly the same. I've just introduced two parameters into the problem. t0 might be free, tf might be free. In any case, it doesn't matter because it gives me the same setup as what I had before. I've just got a scale factor of tf minus t0 over 2 in front of the whole thing. So we'll stop here, and that's it for this lecture, and we'll pick up the discussion next time when I'll talk a little bit about costate estimation using these approaches.